Okay, so another one here. So this one here, so they tell us half-life is 6.8. Its activity is 100 years. So 6.8 is, or 100 is not a multiple of 6.8. I can double check that. 100 divided by 6.8. It's 14.7, so it's not quite 15 half-lives. So what would the activity be? So let's just plug it in. So n naught a half t over p. All right, so I'm just going to replace the pieces I know. So I got 490,000 here. So I'll just leave it as scientific notation this time. Times a half to the power of 100, the time that has elapsed in years, divided by this. That's in years. So the years would cancel each other out there anyway. Okay, so this would be 4.9 times 10 to the 5 to the power of, or times a half to the power of approximately 14.7 ... So I'm just going to pull my calculator out here. It's just on the other screen, so you can hear me clicking away on my mouse. That's what I'm doing. I'm going to put my answer in there. So I'm not going to use the just 14.7. I'm going to use all the decimals there. So after 14 or so years here, or so after 100 years, I'm going to have an activity rate of 18.3 becquerels. There we go. Not too bad. What fraction of polonium remains after 172 days if the half-life is 138 days? Now, fraction is a key here. Sometimes they ask you what percentage is left over, what fraction, what proportion is left over. In this case, we just had to make an assumption what n naught is. If they say percentage, we say 100%. If they say fraction, we just say 1. That's not too bad. And then I can change it into a fraction later if I can, or I just leave it as a decimal, my answer. So n naught is going to be 1. I got a half here. And then over here, I have 178 days, 172 days, sorry, has elapsed. And my half-life is 138 days. Days will cancel out, so that's good. So I'm just going to go a half raised to the power of, and I just leave it at my decimal or my fraction there. 172 divided by 138. And we get 0.42, yeah, let's go 22. As the proportion that's left over, my fraction that's left. So you can't really put it as a fraction. Looks pretty irrational to me. I don't think we can. If I go math, enter. No, it leaves it as that. So we're just going to have to leave it as a decimal here. You can probably say like 42% is left over. If you want to change it into a percentage, that's fine too. As long as you put the units afterwards. So you could say 42.2% is left over, as long as you add the units. Carbon-14 has a half-life of 5,730 years. How long will it take for the quantity to drop to 1/8 of its initial quantity? So what they want, so 1/8 of its initial quantity. So you just have to determine what is my initial. Now, if I say my initial quantity is 1, like I was saying before, it doesn't really matter what your starting point is. The time to get to a half is always going to be the same. So your starting point can be whatever you want. The time it takes to get to 1/8 will also always be the same. So my n is going to be 1/8. All right, I could put 100 there and put 100/8. I could put 200, then it'd be 200/8, etc. There's always going to be 1/8 amount. So we set up the equation. So let's put the equation here. So 1/8 is equal to 1 times a half t over my period. I'll put my little period over here. It's 5,730 years. So it's going to be in years there. Now this is where we get a kind of tricky situation. We have to solve for something that has the unknown in the exponent. Now, if you've done math, to solve for things that have an unknown in the exponent, we would use logs, right? Other ways you can solve it, we can graph it to solve it. We could do a few other different ways to do it. But the easiest way that Physics 30 has set these kind of questions up is that they always make it so that what's left over is always a whole number of half-lives later, okay? So what I mean by that is that if I start off with 1, so this is time 0, 1 half-life later, I'm going to have a half, right? 2 half-lives later, there's always going to be a nice whole number, so 2 half-lives, so whatever 2 happens to be here. What's that number times 2? So 11,460 years. So this is the second half-life. So I just added 5,730 to this number here. I'm going to have a quarter left over. Okay, that's good. And then another half-life later, so I'm just going to add 5,730 to this, 17,190 years. I'm going to have another half of a half, so half of a quarter, sorry. It's going to be an eighth. So the time that elapses is 17,190 years. Okay. Now you could do this on the calculator too. So we set up the equation, so that's good. So if I want to put this in my calculator here, let's move my head out of the way. I'm just going to turn off some things like this plot here I don't want turned on here. So I'm going to have 1 bracket, a half bracket. In my exponent, I'm going to have x divided by 5730. Okay, I think that's the right number, right? Yeah, 5730. On the other side of the equation, so we're going to graph the left-hand side. We're going to graph the right-hand side as 2 different equations. So I'm going to put 1/8 on this side. I'm going to graph that. There's a line. That line is my exponential graph. You just can't see that as decaying because my domain is way too small. Like this is in the x-axis and my time axis is in years. And I know my solution, it should be around 17,000 years. So what I'm going to go to my window here and change my x max to be somewhere around 17,000. So I'll just say 20,000 here. Okay, so now it went down. And then here, my starting point is 1. So I'm just going to change my window to not have so much y max. So I'll just start at 1. Let's put a 1 there instead. Oh, I got all this bottom part of my graph too. I don't have any negative parts to this graph. So I'm going to make my y min 0. Ah, looking good. Looks pretty nice. You can see there's a little crossing point. So this is my 1/8 line that popped up there. So I'm just going to second trace, intersect, enter, enter, enter. And you can see I get 17,190 as well. Cool. There we go. So what percentage will remain after 8,000 years if my half-life is 1,600? So I'm just going to double check. I'm going to take that 8,000 divided by 1,600, and I get exactly 5. So this is 5 half-lives later. So I should be able to determine percentage pretty easily here. My head's that over here. Okay. So 1 half-life. I'm just going to put 1 half-life. Let's call it HL for now. Whereas 0 half-lives, I've started off with 100%. Okay. 1 half-life later, I'm at 50%. 2 half-lives later, I am at 25%. 3 half-lives later, I am at 12.5%. I'm just dividing by 2 each half-life. 4 half-lives, I'm at, I don't know why, I don't want to do the math in my head here, 6.25, right? Yeah, 6.25%. And my last half-life that I want to deal with here is going to be whatever this last number is divided by 2. So 3.125. 3.125%. Now, how do we know it was 5 half-lives? I just went 8,000 years divided by, remember to find my n value, my number of half-lives, divided by my period, my actual half-life. Years cancel out. And we got 5 half-lives. Oops. Some final answer, 3.125%. And again, you could just plug it into your calculator. Well, Or this one here, you could just set up the equation. I don't know what I was thinking. Like I could just set up the equation, said, okay, n, I start off with 100%, a half, and then up here I could say 8,000 divided by 1,600, which is 5. And just the math on that, it'll end up being 3.125% as well. Yeah, I don't know why I did that the brute force way, but you could. All right, so that's the gist of half-lives. Now, one thing that's kind of missing here is how did you determine the half-life? Because in the lab, you're going to be doing this determining the half-life thing. Now, determine the half-life is pretty easy. Once you do your regression, once you find your curve of best fit, now you can't do a line of best fit, you're going to have to do a curve of best fit. So you're going to do an exponential regression, not a linear regression. So I'll show you how to do that in the videos attached to the lab. So I'll do that in the lab part. So once you got the regression, you determine the starting point. So determine the y-intercept, right? It could just be that data point there. This ends up being 2, but the regression may not be exactly that. The regression will be whatever the y-intercept happens to be in the equation, which is whatever's in the front here, this n naught. Right? When you do the regression, you're not going to get a half here, but this n naught always represents the y-intercept. This represents the y-intercept. So this beginning number in front of this exponential is always going to be your y-intercept. Then what you're going to do is you're going to take that number that you found, divide it by 2, and create a line on your graph and find out the intersection point. And that intersection point is going to have time, which is going to be your half-life here, comma, whatever this activity that we used here. In this case, would be, in this one, would be 1. In this case, right? So you're going to graph those two things, graph y1, graph y2, and determine that intersection point. You can probably just view it right off the graph if you have a nice grid, and you can see that. So you take the top, first number here, divide by 2, and that is going to be that. You can take any number. So you could technically take this number, divided by 2, whatever this number happens to be, and then that would also be the half-life too. But this one's a bit harder to read because there's no grid, so I wouldn't use that point to do that. Okay, so that's that. So you can either try the lab or just continue on with the next video and talk about fission and fusion, and I'll see you then. I gotta turn off my, there we go. Oh, sorry about this video, it took longer than I thought. Maybe I'll split it into 2.